Good afternoon. Welcome to the 4C Conference webinar series. Our presenter today, Arnold Rivas Griswold with Fluenta. Arnold is a petroleum engineer from Texas A&M. He's been with Fluenta for 15 years. Fluenta has been an exhibitor and a partner of 4C for the most of the duration of the conference. We very much appreciate Fluenta's support. We much appreciate Arnold's presentation today. And again, we also appreciate all the attendees on the webinar today and very much appreciate your historical support through the years. If you have a question, there's a button up in the right-hand corner with a conversation icon. If you click on that conversation icon over on the right, will appear the chat line, and I am going to type your question over in that box so that everyone can see. There you go, over on the right. If you have a question, type your question here in the chat box. At the end of the presentation, I will then look through all of those questions and present the questions as a moderator to Arnold. So without further ado, Arnold Rivas, take it away.
All right, thank you very much, Steve. Good afternoon, everybody. Thanks for joining us for this presentation. I would like to have a chat with you guys about best practices, or I would say also different considerations for selection, installation, operation, and maintenance of flare gas meters. As you know, this kind of measurement has been regulated by EPA for a while, and also there's local requirements and local recommendations by TCEQ and other entities, and we also follow API 1410, which has been the standard that's been around for a while. And I think recently it's been under review for further compliance and consideration. So I'd like to basically cover. Give me 1 second to. There we go. So I'd like to cover this agenda. So I'd like to, first of all, we're going to cover the basics, which is why, when, and what we measure, when and why we measure, challenges involved in the flare measurement per se, the process, selection process, installation, operation and maintenance, and then we're going to have some time towards the end, like Steve mentioned, to cover questions. So first of all, what we measure is different sources apply for the flare gas measurement. So in the different applications associated to it involve petrochemical plants, refineries, gas processing plants, generally oil and gas production facilities onshore and offshore, storage facilities, and also LNG facilities. So I mean, the flare has been used over time as a safety mechanism to handle different situations, and those situations basically represent unit upsets, problems with compression, maybe relief valves, and startup and shutdown operation, blowdown operations, and such. So many of these situations will have the gas being sent to the flare line, the flare header, and then the only way to account for that gas in terms of mass balance and in terms of emission reporting would be to have a meter in the flare line to be able to account it. So, like I said, I mean, flaring is typically a safety measure. I mean, whenever we have either an emergency or a planned situation where you have to dispose of the gas that you can handle in the facility, that's when we get the flaring situation we have to measure. So now I'd like to cover some of the challenges that we see with this kind of application. And we'll go a little bit more in detail, but some of it is the velocity range is very wide. I mean, in normal operation, you have a low velocity because you don't expect to emit that much gas, but in an emergency situation, you may have large quantities of or large volumes of gas going to the flare line, and you have to be able to measure and account for it. Because that volume can be very big, sometimes you have to design for large pipe diameters. So that's another consideration. And of course, because the gas may come from different directions or different sources within the plant, the gas composition may vary depending on the situation or what compressor went down, what unit is in trouble. So you will have changing gas composition all the time or most of the time. When it comes to ultrasonic measurements, which is what Fluenta focus on, there's also noise and noise considerations and the signal to noise ratio that we have to take into account when it comes to our measurements. So that's something that has to do with the velocity and the properties of the gas that's going through the pipe. And of course, I mean, everything that you use to measure will be exposed to erosion and corrosion based on the fluids going through the pipe. So some considerations, for example, in the selection process would be, like I mentioned, the pipe size, velocity calculation, and gas composition. So let's take a look at those in detail. So definitely large pipe diameters can represent a problem. So in different situations, we have to design for the worst case scenario. So or engineering companies will have to design for the worst case scenario. So that means that within an emergency situation, they will have to define what kind of volume they will have, potentially what kind of gas composition they may have from different units, and then based on that, define the pipe diameter. But what's going to happen is that that's one situation that may happen, I don't know, maybe less than 1% of the time, the operational time. But then the other 99%, you're going to be flowing very low flow or mid-range flow, and you have to have a meter that's able to handle that. So within a large pipe, you'll see different flow regimes depending on velocity. And especially if you have velocities fluctuating from such a big range, that becomes a challenge in terms of measurement. So that's why, for example, many of the pressure drop devices are not necessarily ideal for these kind of applications, because sometimes they don't have the turn down ratio that is necessary for to handle the low and the high velocity range. So something to consider when designing for the application, or when defining what kind of meters you need for the application. So like I mentioned, I mean, sometimes you have very, very low velocities, and those low velocities can create asymmetric flow regimes and, induce cross flows, sometimes, backflow. And at that point, I mean, you have to be able to still measure that. Yeah, and this covered the high flow. I guess I touched on that during my chat. So the other part of the selection process would involve the gas composition. So like I mentioned, sometimes you have a common flare header, but this is fed from different units, right? And each of these units will probably handle different compositions, different gas compositions. So at some point in time, you will have just one unit to go down, or you may have several units go down, and then all of that gas will be commingle in the main line, and you have to be able to measure it. So normally what happens, you have changes in densities, you have changes in molecular weight. It can vary over time, and the proportions of those different gases will vary. So you have to be able to find a measurement principle that's going to be suitable for those changes and equipped to handle those changes. So let's go. Well, in this particular topic selection, between the pipe size, velocity calculations, and gas compositions, are there any particular question before we move on? Okay, I don't see anything in the chat, so I'll move on. If anything, we can handle those towards the end. Okay. So in terms of the installation, there are different considerations: straight run, the orientation, the decision whether or not to use intrusive designs for the sensors, whether you need a spool piece or you're going to do a hot tap installation, and then sources of noise. You have to kind of think about it as well. So straight run, like any particular meter, you need a certain straight run to make sure that at the measurement point you have a fully developed flow profile, or as good as possible, right? So many ultrasonic devices normally require a 20 diameter upstream and 10 diameter downstream. I'm sorry, and in our case, we focus on 10 and 5, which is half of the original requirement. So in a 16-inch pipe, that's a 20 feet of additional straight pipe. It all depends on what kind of facility you're looking at. Sometimes in refineries, on gas plants, sometimes you have a big flare lines, a large, long flare line, and you don't have to worry too much about it. But we face at Fluenta, we basically started in Norway, and we addressed the offshore market, especially in the offshore market, where you have to install these meters on a platform. You have very reduced straight runs and very limited straight runs. So you have to make sure your footprint, when it comes to the meter, it's very small. And so that's why we do a combination of different signal processing to reduce the straight run to half of what many meters require. So that's something you need to consider when selecting a meter. You have to make sure that you have enough space and that the meter you're selecting is suitable for that. So I'll show you. I'm showing a couple of installations, onshore, offshore, different orientations, for example. So you see a horizontal pipe. In this one, you see a vertical pipe. So these ultrasonics meters can be installed in both directions, but there are also some considerations in case you may see some kind of liquid or condensation in the pipe, especially at that point when you're flaring. And if that's the case, you have to take some actions to either correct that from the process point of view. Maybe, maybe that can be handled by a knockout drum and tuning the efficiency of it. But if not, you have to kind of prevent that from or handle that at the metering point. So the most important thing is to try to avoid the picture on the right-hand side where you have liquid accumulation, and then that liquid may be flooding the sensor, and you're covering that sensor with liquid, which is, in many of these, for many of these meters is a problem because they're calibrated to measure gas. So ideally you find a location where you don't have that issue. If you're restricted to a vertical pipe, then there are mechanisms that we can utilize in the meter itself. So it's hard to see from this picture, but we normally have a fitting here that we can use to drain the sensor, at least the upstream sensor, to make sure there's no liquid accumulation, and we can easily send that liquid back to the knockout drum. So there are mitigation factors, but when it comes to installing the meter, there are some considerations. Sometimes we've seen installations where they decide, well, let's make it a slanted installation to make sure that if there's any liquids, then they will probably drop down the line. But it all depends on what kind of situation you have, and what kind of flexibility you have in order to install the meter. Another decision you have to make is whether you can use an intrusive design or a non-intrusive design. So ideally, because these sensors are exposed to both low and high velocities, and sometimes very rapid changes in velocities, sometimes you don't want them to be exposed or intruding into the line and be exposed to those velocity changes. If you do, though, you have to make sure that you have the right calculations done, the wake frequency calculations, so similar to what we do to a thermal well, to these sensors, so that you can analyze the stress from rapid changes in velocities and avoid those sensors from bending, or prevent these sensors from bending or just breaking inside the pipe. But ideally, we suggest this kind of installation where you have the sensors flush to the pipe wall, and that way you don't have a big impact from velocity changes, and you can easily handle those velocity changes in real time. So the next consideration will be the decision to buy a spool piece or do a hot tap installation. So many of these ultrasonic meters, because the main principle would be the transit time of the signal, and these sensors, or these, this is not the best picture, but we'll see it later in another slide. So we'll be sending signals back and forth between the two sensors, and we measure the transit time to that's later correlated to velocity. But then you need a certain angle in relation to the pipe. So typically it's around a 45-degree angle, so you can get the best signal, and you get a signal going with the flow and a signal going against the flow, and that differential will help you calculate the velocity. So what I'm trying to get at with that is that angle has to be done as precise, as accurate as possible, right? So you get the best accuracy when you make a spool piece for these kind of applications. So this is measured carefully and in the shop, and the angles are reviewed and calculated properly. So at the same time, there are ways to do it on a hot tap operation. I mean, there are many companies that are very proficient in doing that. We normally work together with them to try to make the markings in the pipe and make sure that the angles are correctly calculated or estimated. We use the proper tools like a welding jig for the different angles, and basically do a little hand holding with the welding people so that they can, not only do the have the location in the right place for the nozzles, but also make sure the angle is correct. So those are the two options. I would say probably 95+% of the applications we do are with spool pieces, because they want to make sure that these the angles are correctly calculated and the welding is more precise. And at the same time, you may want to reduce the uncertainty related to the installation by doing that. So there are two options depending on the facility, but of course we recommend the spool piece version for it. Okay, so as we go down the list, we get to the operation and maintenance. And there are several considerations: the inputs, the outputs, process conditions, erosion, corrosion, calibration, etc. So let's take a dive into that. So sorry, this one is a little busy, but the purpose of this slide is to show more or less the variables that we're looking at. And when it comes to the inputs, it's fairly simple. We need the flow computer needs an input from the transducers, but also we have pressure and temperature measurements on the line, and basically we take those measurements as part of our as an input for our calculations. Now, when it comes to outputs, we basically we can focus on these lists that we have here. So we can show the standard volumetric flow, the actual volumetric flow, mass flow rate, density, molecular weight. We can set up alarms in case you want to set it up to an emergency situation or maybe an overpressure situation. Same with temperature, in case you want to handle like dew points and stuff like that for condensation. And we're monitoring that. So we have different outputs. We have analog and we have Modbus digital outputs. We can convert those to different interfaces. It could be serial interface. It could be TCP/IP interface. So this is more talking about the features we have, but just to make a point that when you're selecting a meter, you may want to take a look at your overall design in terms of the control system and everything, and basically do a good assessment with your flow measurement manufacturer and decide which one is the best way of connecting to the DCS. So like I said, I mean, many of the manufacturers out there will have different options, either analog or digital, but what gives you the best value? That's what it is. In many circumstances, I would recommend Modbus, because you're not limited to a certain amount of outputs. So basically, you have the whole array of variables available in Modbus, and you can pull from these data, from these variables as you wish. And then you can have that information in your DCS, and then you can do calculations and stuff and make sure you get the data you need. So, okay, so that covers this part. Another important area when selecting a meter is the process conditions. So we normally do an assessment when we first receive an inquiry for flare meters, and that assessment will include the expected gas composition. Sometimes that gas composition will have different scenarios. The emergency scenario, it could be the normal scenario, or probably the purge scenario. So we take those into considerations to anticipate what kind of impact we may have in the signals and the things we'll see during operation. So, and if you see the picture sometimes, because the flare line is not necessarily the cleanest line in the facility. You see sometimes liquid formation, so sometimes you see coating from different elements that go with the gas. So you have to definitely take those into account. Not necessarily for performance issues, but it could be the case in some situations. But the main thing is to anticipate the maintenance frequency. So how often you go back to the field and, for example, pull the sensors for cleanup or for a verification process. And that's something that you learn over time as you operate and maintain the meter based on your flow conditions, based on your process condition. So that's something that needs to be taken into consideration. Many people during the selection process, they ask me, okay, how often do you need to pull the sensors to clean them up? And we normally say once a year to sort of be on the safe side. And there's also recommendations from API and EPA to go back once a year and verify it. But at the end of the day, it depends on the process conditions. So I think it's really important for the maintenance people and also the people selecting the meters to take that into account. So the next aspect of it is the material selection. So if you're telling me we're going to be in a sour service and very corrosive environment and all of that, so we may have to select a material for the wetted sensors that is a little bit more sophisticated. So more sophisticated alloys, and we have the ability to use. Normally, we have titanium, like the rod of the sensor rod would be stainless steel for the most part, and the tip is made of titanium grade 2. But if you have a situation or an application with a very sour service, then you may want to consider other alloys, Inconel, Hastelloy, et cetera, or maybe duplex could be an option. But of course, that increases the price of the sensor. So that's something we want to address with the customer early on, so they can really assess the risk and benefits of having those or getting those alloys. And another rule of thumb is to probably make sure we take a look at the pipe side of the pipe materials and try to match the specifications of the pipe material, because I mean, if you have a service that requires a spool piece that's going to be stainless steel, we know it's going to be a more sophisticated kind of process that we have to take into account. So, I mean, generally speaking, I mean, this is very common sense, but sometimes in terms of going through the selection process, things may not get discussed early on and may cause problems. So that's why I'd like to bring it up here. Okay, so part of the process is also the calibration, and there's a lot of conversations related to calibration. How do we do it? Do we do it? Do we do an in situ calibration? Do we do a factory calibration? Do we take it to a lab to be calibrated for certain conditions? So when it comes to flare measurements, it's really tricky because you can get in many applications, you can get up to 300 or plus almost 400 feet per second in velocity in an emergency situation. And I'm talking about probably a very, very significant volume in terms of the facility capacity, right? But at the same time, the meter has to be able to go down to 1 meter per second or less, right? And the question is, because it's really difficult to replicate those kind of velocities, especially on the high end in the field. The question is, okay, if you're going to calibrate it, what do you calibrate it for? Because in many cases, you don't really have a good reference that can go that high in terms of velocity. So what are the options? One option is to calibrate it in the factory, to do a factory calibration. That can easily be done before shipping the meter out to the facility. But you have to take into account that calibration will also be limited, because you can't really take the meter in a lab to 120 meters per second or 400 feet per second. So it's really difficult to achieve that based on just capacity, right? And you can take it to, in our experience, we've taken meters to CC, for example, and they have a way higher capacity to do this, but it's still probably limited to sometimes like 50, 55 meters per second. Can't remember what that is in feet per second, but you can do the math real quick. So it's very limiting sometimes because of the nature of the flare series. So you have to take into account. So typically the required accuracy for these kind of meters is, to be plus minus 5% or better, right? Usually it's not a custody transfer point of measurement, but it's because it's emissions, it becomes, it's relevant, of course. So many companies sometimes aim for better than 5%. So typically our range out of the box, our range goes from 2.5 to 5%. And if we need to do a calibration, we can do it, take it down to a 1% maybe. But again, it's going to be based on that velocity range that we can handle during the calibration. So just keep that in mind. And sometimes the cost of sending this to CC and all of that, I mean, it all depends on what you want to achieve, but it has to be done properly to really justify the cost of doing that for just a limited range in terms of measurement or velocity. So what do we do on a regular basis? So the verification process or the validation process is just that, more than a calibration. It's just verifying that on a yearly basis, say, or maybe, if you determine based on the process conditions, as I mentioned before, that you have to go, on a more frequent basis. You go there, you pull the sensors, put them in a zero box, and then in that zero box, temperature is controlled, pressure is controlled, and there's no airflow. So you know that what you're getting there, you're measuring air, so you know the composition of air, and you know the speed of sound of air, right? So you can compare that speed of sound with the speed of sound that you're measuring with your device. And at the same time, you control all the other elements, like, for example, the distance between the two transducers. That's something you have under control. You know that, and you fix those elements, and you get a good zero verification. If there's any drift over time, you can easily offset that, as long as the meter or the sensors are still healthy and and the signals are strong enough. So that's what we do. And then we can do a variety of diagnostics involving the signal quality. And we see the amplitude gain, signal to noise ratio, and in the speed of sound, like I mentioned before. So those are the kind of things we do. So this is an example of the components of the flare meter, the Fluenta flare meter in particular. So you see the field computer right here. So this is the brains of the system. The canister you see here, the cylinder, contains all the electronics. So the signal processing, inputs, outputs, everything is managed here. But like I said, signal is processed here. The signal is generated, is sent to, for example, this upstream sensor, is shot through the medium to the other side and received by the other sensor, and then it comes back to the flow computer. And it's also analyzed here. And when that signal is the same signal that we send is verified receipt here in the flow computer, we take the time of flight. And then we do the same process through the opposite side, and then the time differential will help us determine the velocity. We may add a mounting frame to make sure we have that flow computer close to the sensors. We have a certain distance that we can provide for these cables. So it goes up to about 30 meters. And, with that, you can put the sensor or the field computer in different places. But, typically, I think the standard is like 10-meter cables. And then we have pressure, temperature measurements. Like I said, those are part of the inputs. The other inputs we receive are from the sensors themselves. And then, you see the spool piece. This is a spool piece version. So one little thing about this arrangement here is that we have a ball valve connected between the nozzle that's welded to the pipe, excuse me, and the sensor. The idea with this ball valve is that we have the ability to retrieve the sensor online without shutting in the pipe or stopping the process per se. On a regular operation, nobody wants to stop the flare line. So that allows us to pull the sensors and safely basically remove them and put them in a zero box to do the calibration or the verification that I mentioned before. So when it comes to measurements, there are different ways to tackle that, and it all depends. Sometimes you want a better accuracy. In those cases, we may offer a dual path arrangement. It can also be done in a way that it gives you redundancy. So you can make a selection depending during the selection process. You can express whether you want better accuracy or redundancy, or maybe you want a little bit of both, and then we can play a little bit with this setup to give you the best results. But you see the setup is exactly the same. The only difference will be that you will add another pair of transducers and ball valve and everything to be able to achieve that. So that's an option you can pick, you can select nowadays. The other thing is, depending on the process condition and depending on the type of the application type, we can select different sensors for your application. So we have the standard transducer. It's really suitable for, I would say, 90 to 95% of the applications. So this is a set of sensors that goes from 0.1 to 394 feet per second. So like I said, very wide range. So these reflects basically a 4,000 to 1 turn down ratio, which is more than what you normally see in any other type of measurement. So I would say it's basically flare measurement that requires this. So the accuracy varies. Like I said before, I mean, we normally go from 2.5 to 5%, but you can get it down to 0.75% if you start doing calibrations and different configurations, especially for dual path. So it's customized depending on the application, really. And in terms of the pipe sizes, we talked about the challenges involving the large pipe sizes. So we can offer meters that are going to be able to measure pipes from 6 inches to 72 inches. And then we have some larger pipe sizes that we can probably achieve with this other meter right here. So I'll talk a little bit about it. In terms of operating pressure, we are normally operating at very low pressure because basically this is exposed to atmosphere, right? So at the flare level. So 145 psi is the kind of the general application. When it comes, probably close to the time, but when it comes to the different meters, so I mentioned you have the standard transducers, but then as we get to different applications, as we get through different applications, we see gases that are more challenging to send the signal through, and those are typically, especially CO2. Sometimes when you have really high methane, especially 100% methane, like LNG plants and stuff like that, you see this challenge. So we have the ability to use a different set of sensors that has an enhanced signal processing and a stronger signal per se to be able to deal with those. So basically the other configuration or the other specifications are quite the same, but these will have a signal strength at a different level that will allow you to deal with those cases. And then we have flare phase, which is another set of transducers that not only allows you to handle those denser gases, but also allows you to go to more extreme temperatures. So now you can go to minus 196 Celsius especially for LNG application, and up to 250 Celsius for other applications that require that. And hopefully in the future we'll be able to increase that a little bit. So more to come towards probably mid-year or towards the end of the year. So just going really close to the end. So I just wanted to show a list of the companies that we've done business with and we're doing business at the moment. Some of the installations we have worldwide. And then just, Fluenta, it's a global company. So just to give you an idea on the reach we have. So here in the US, we have the company based in Houston. So from Houston, we handle North America and South America. We have Fluenta Solutions in the UK, handling all the European and Middle East area. Poland is actually our factory in Dubai. From there, we handle Middle East, and then Malaysia, we handle Asia completely. And then, our headquarters have been in Norway traditionally. The Fluenta is a private company, and the owner is Norwegian, so that's officially our headquarters. And finally, to be able to contact Fluenta here in the US, here are the contact information. Well, I appreciate the time. Thank you, everybody. And, I'll leave the room for questions now.
Thank you very, very much, Arnold. It doesn't appear there are any questions. So this will conclude the webinar. Thank you very, very much again for your time. We're running right at 1:50, which is perfect timing. We appreciate the support of Fluenta and appreciate the support of all of our many exhibitors and sponsors and attendees. And as we noted earlier, the 4C conference this year now is scheduled for August 18th to the 20th in Austin, Texas at the Hilton. Everyone will get to enjoy Austin in the summer. Hopefully, it won't be too hot, but you will get to see the things that you normally don't get to see when we have the conference in February. Wonderful things like Barton Springs, Hamilton Pool, and Deep Eddies. So look forward to seeing y'all in Austin in August, and appreciate your time and attention and consideration today. Thank you all very much. And again, thank you, Fluenta, and thank you, Arnold.
Thank you, Steve. Have a good one.
Take care.
You too.